So we constructed 26, and I can kind of talk you through it because we set it up. I think I posted on Canvas those trig, yeah, like I made PDFs of my slides, so if you forgot those trig identities or something already or didn't write them down, you can pour through Canvas for them. So 27 is basically the same problem. It's the same setup. Now it has numbers and stuff to calculate. I think we're calculating the coefficient of friction. If it just slips, that means it's exactly equal. So the forces will be exactly equal when a painter has climbed 70% of the way up the top of the ladder. That means she's 70% of the way along the hypotenuse. Just multiply the hypotenuse times 0.7, and that's how far along she is. No problem there. But what forces will that affect? How will that change 26 that we basically wrote down in your notes yesterday? If we can get some ideas, then I'll turn you loose. Okay, there is an extra mg. So let's see. How would I write it? Yep, I would do that. Located where the painter is, you can just do another one that's like big mg. You can use g for 10. 10 for g, that's fine. Let's just draw it bolder, since I didn't make room for my bigger arrow. Okay, so there's also that. So that thing will have its own torque. This is 27, by the way. 26 has no painter, it's just the ladder, or the meter stick leaning there. Mine's still standing up, okay. Solved it successfully. This is 27. So, excellent. There's another heavier mass now, not at the center of the ladder, or the very end, but 70% along. I think you can figure that out. But that changes some of the other forces. Okay, and what you might immediately do, I can scroll back up to the picture in a minute. Yeah, my colors won't match yesterday. Just start modifying your equations. So it's still equilibrium. The vertical forces still have to add up to 0. But now you have normal force minus little mg, that's the ladder itself, minus big mg, that's the person. So obviously the normal force will be more, will have changed. Okay, what other forces does that affect? That's what I gotta make sure you have a running start. I don't want tearful emails. I don't even read them. At 11 o'clock tonight, nope, I get up at 5:30 the next morning and read them. It's too late. Let's see, I spot two things that it should change. Sure, Abraham. Yeah, so the coefficient of friction won't change. We didn't change any kind of structure, but just because there's more pressure between the ladder and the floor, because someone's standing on it, okay, force of friction increases. I'll let you calculate it, but you better expect more than if it was just a ladder. Okay, and you determine this new bigger force, normal force, plug it in there, and then we go. Okay. Someone else. Just because, oh, I thought of another one. If that increases, then there should be another immediate consequence to that one. Let me pick on him, Abraham. Let's see. Landon's looking down his lap suspiciously. Landon, what force? How come the friction force can't, like, slam the ladder through the wall? Okay. The wall, if there's more force of friction pushing to the right, the wall should have to exert some more force too to maintain equilibrium. Okay. That's the easy one. If there's one more thing, there should be more. There's an extra term that now has to be added. Like there's an extra term in this Fy. One of the other equations, f of x won't even look like it changes. It just has, you had Fw, and Fw is just more. If someone is on the ladder, there's an extra mass there. What happens? really have to recalculate everything. What was our, with just fx and fy, we couldn't even get this problem started. It didn't have anything to do with angles last time. Yes, Landon. Yeah, this has its own torque. The painter herself. Okay. There's a new torque just because of the painter. Her lever arm will be 0.7 times L, the length of the ladder. It has an actual value for 27. And then times mg. Oh, times the sine of some stuff. Let's, oh no. I learned to use technology, I really did. Yeah, like that. Scoot this over just a bit. What was the angle between the ladder? It's not theta. I need the sine of the angle between there. And I'm going to trick myself on these last two problems if I just call everything theta. Between the ladder and gravity, it's the same as 26. Is that the 181 or is that the plus 90? It's 90 plus. Okay, good. So it's going to switch to cosine. If you're a super trig all-star, you could, I guess, switch it to cosine right away. Okay? But good. Alright, that's the point. When there's some person climbing up the ladder, of course it has to increase the normal force because they don't smash the ladder through the floor. But that also means you should expect the force from the wall to increase, both so that the ladder doesn't move side to side, and because there's now an extra torque to resist, right? A person up the ladder tries to swing the ladder down. There'll be some more negative torque. Okay. Well, if you account for all those things, then you should be able to solve 27 as well. And if you're making progress on the assignment in class today, hopefully, because it's due at the start tomorrow, we're going to collect assignments and get started on this lab. Let me know. I'll tell you if you're right or wrong, at least. I'm not sure I'll tell you what the right answer is. And if you ask really nicely, if lots of people are getting like number 6 wrong, I could show you. Okay. Any questions at this time? Okay then.